Gentlemen, welcome back to the Empire of Dirt here in the frozen shithole of Hoth. You probably can't see this, but I'm wearing gloves. And we have a shock we are going to disassemble and inspect. This is a rear shock off of a mountain bike. Fellows were asking me to do Kashima front forks just to see if they were any fucking good at all. Well, I can tell you for $2,500 hairs for a bicycle front shock, there you're essentially paying for market wanketeering, and I'll tell you why that is. But in the interim, I changed the rear shock off on my minimum viable mountain bike, the Norco fluid minimum, whatever it's called. Craptacular shock on the rear of her because there's no lockout for climbing. What you want to do for climbing, of course, you want the solidest frame going because you want all your energy, what you're pedaling, into turning that rear wheel instead of into compressing a shock. Now this is supposed to be the best of all worlds, tuned for every condition. Of course, we know that never works, so I changed the shock out for a better shock, what actually has a lockout, and figured we'd sacrifice this one to the teardown gods. Outward countenance proving that there is nothing new under the sun, exactly what you would expect in a commodity item. A die-cast aluminum housing here, anodized black, CNC machined, and then the rod itself has been polished to a higher bit of sheen, but also die-cast aluminum. That would be a high silicon aluminum so that we get quick nucleation and nice small grains. And we see they did a nice job here on the finishing. There's no, yeah, you see that sheen there? There's no big chunky marks from grinding with a heavy wheel. That actually has been honed. And then in the backside here, machined, bored out to size, and added a DU bearing, which is essentially just a Teflon bearing inside a metallic sleeve. You can see the metal sublying it. Appears to be some sort of aluminum bronze, maybe full-on bronze. Aluminum bronze is better at abrasion, which you'd expect in a mountain bike application, or you know, a motorbike or any kind of thing like that. Again, same thing in the frontwards, offset by 90 degrees. We have a Buna N nitrile rubber O-ring here. It's not that it came out. They leave those on there so you can see where your shock bottoms out. That's a measurement tool. And a double lip seal here, or possibly single lip. We'll have a look with the flare towards whatever you want to keep out. So anytime you have a seal and you're wondering which direction it has to go, you got to think about the application. In this case, this seal is a wiper and we want to keep out the shmoo, so we leave the flared part out towards the shmoo. You can see plainly with your eyes there is some lubrication on there. We're going to come back to that when we get discussing the Kashima coating. This being in essence an air cylinder, you have no adjustment for the speed of compression. You'll only have the adjustment for the speed of extension. A ubiquitous and beautiful piece of engineering here, the Schrader valve. These are essentially one-way check valves that are manually, well, you put a pin in there and it opens it up. We'll see if I took the pressure out here already. No. So it's important in accumulators or anything like that to make sure, which this is, a pressure vessel, to make sure that there is no residual pressure. Now there is another type of valve that does the same feature as this, as a Schrader valve. Now the Schrader valve, ubiquitous in industry because it's very high pressure. It's capable of withstanding 5,000 PSI, no problem. And we see those in nitrogen charged accumulators as well. On the bicycle side, we also have Presta valves, which are quite a bit longer and smaller in the dingus end. And what that allows you to do, those are specially formulated so that you can unthread them and drop pressure off just with your finger. You don't need a special tool to get in there and drop the pressure off. Of course, you can't. The only way you can add pressure is by pumping air in there or nitrogen. But here is the core of the valve, and all there is in there is a spring-loaded check valve. And when you push it down, it opens the check. The rod is going to be hard anodized. It should be, in any case, if this is any fucking good at all. And this will be just a easy, light sanitizing. Don't quote me as sanitizing, anodizing. Okay, the reason why aluminum does not rust is not because it doesn't oxidize. It does oxidize. It forms an impermeable oxide layer because the oxide, the crystal structure of the oxide is very close to the crystal structure of the base metal. Wherein, if you look at something like iron, the oxide crystal structure is very different than the base metal, and it causes it to slough off. It causes the oxide to slough off because the crystal structure is so very different. And that is why we see rust in steel and iron, but we don't see rust on aluminum, even though it does oxidize. That oxide layer protects, it forms a impermeable layer that protects the base metal from further oxidation. So we take advantage of that in aluminum in order to prematurely oxidize it to different thicknesses to provide some modicum of protection from abrasion and further oxidation. So in this case, what we have is, don't quote me on this, but mil 8625, I would say, is the spec. And it's got 3 types. It's got type 1, which is done in a chromic bath. Now, when you anodize these, what you're doing is you're passing direct current through this workpiece, through the anode, cathode. They change depending on if it's a battery or, I always get mixed up. It's like my right-left dyslexia. I don't know if I'm turning, is it my left or your left, So in this case, very likely it would be a type 2 anodizing, which means that it's forming pores in the material, and it's also thickening that oxide layer. Now that oxide layer might be but 1/1000, say 25 microns. And those pores that are created, and I'll put a little thumbnail here. You can see the pores in a scanning electron microscope. The pores are but 10 to 100 nanometers in diameter. We're talking a 64th of a blonde one, a strawberry blonde one at that. Now on the hard anodizing, what we do is we leave it in the sulfuric acid bath, which is type 2 and type 3 anodizing, and we leave it in for longer, and that embiggens that thickness. So what we're looking at here, and just let me prove it to you. If we look at that one, that comes off pretty easy. On the back side here, it's a totally different process. That's been painted with a plastic powder and then baked on powder coating, they call that. And that's also done with the aid of electricity, very high voltage, that causes that powder to stick to the part, and then they cook it in an oven and it melts all together. But this section here, anodized. Now look at the difference. I scratched that pretty good. Now I take a scritch of this, and it's quite a bit harder. I really got to push on that to break through that oxide layer. This black color is actually, it's dye. And it's dye that's been injected into, well, not injected, but it's been taken up by those little tiny pores in the material, and then it's been sealed. So even if you wear that dye off, a lot of times you still have the hard coating, you still have the oxide layer, but it's just that the dye has kind of worn off, and we see a different color of dye here, red dye, and then this would have been sealed. Now here's the thing about the Kashima coating. Kashima, pardon my French. So that gold, that gold Kashima color is actually total, well, it's not bullshit. What it is dye. It's been dyed and sealed a gold color. Now this Chinesium mag base is not super high end. It's just been dyed a gold color. No big deal. The dye is in the pores and then sealed up. It's not indicative that this thing is a high performance part. Let's get in here with our specialized spigot knurler. You never know when a oh, not even tight. Never know when a plumbing emergency is gonna break out. You're gonna have to customize somebody's fancy brass taps. So the Kashima, Jesus. I got sweaters on the brain, I guess. Tight ones with boobies. The whole claim to fame is that the pores of the Kashima aluminum has been impregnated with molybdenum disulfide. But recall what I said not moments ago, the pores are so tiny on the nanometer scale that it is difficult to anodize aluminum white because you cannot get a dye molecule small enough to fit into the pore. So how in the fuck are they getting molybdenum disulfide? Molybdenum disulfide has a structure, the molecule has a structure much like water, where you have two little dingle balls over here and a central thing. When that crystallizes, it crystallizes in sheets. And those sheets are what provide the dry lubricity, because the sheets like to slide one on t'other. What ends up happening is all of the sulfur ions are all towards the outside, form a nice flat sheet, and you put sulfur together on both sides. They don't want to stick together. They're forcing each other apart, and that makes it kind of slide real easy. That's what the molybdenum disulfide does. Unfortunately, those platelets are far too large to fit into the pores in the anodized aluminum. So I call bullshit on that. But I set to looking at some of the patents. This was a while ago and from memory. So what they're doing is they are taking molybdenum sulfide and they are using it in the anodizing process so that when the molybdenum disulfide forms, it forms in the pores of the aluminum. Now I have a little problem with that because you need platelets to form in order for them to be able to slide together. Also, if you take a hard material, you drill holes in it, and you put a soft material in those holes, where's it going to bear on? Is it going to bear on the soft material? No, it's going to bear on the hard material. So you're always going to be bearing on the aluminum and not that injected molybdenum disulfide platelet in there. Now, as it wears down, you might get some platelets out on the periphery, but that will wear off. In the patent itself here, now I'm getting into it. In the patent itself, it shows some very, very coarse granularity on friction coefficients. But you'll notice they're missing a lot of data there. It's not very scientitious. And what you see is that for dry metal on metal contact, yes, it is quite lubricitous, but the thing is, we always put a little bit of grease on here because you don't want dry friction, dry sliding friction. What you actually want is you want hydrodynamic slip. And in order to reduce the stiction of this thing, there's always going to be some lubrication on that Kashima coating. And they don't show any data for a lubricated plate sliding on a lubricated plate. It's only dry. So there's a bit of wankery around involved in that. And the fact that you got to pay 2,000 American doll hairs for a set of forks for something that, you know, are you really getting your money's worth out of that? Now here we have the first variable volume reservoir, and what we've got in there looks like a Teflon bearing with a quad seal. Now a quad seal is much like an O-ring, except the cross-sectional area, it kind of looks like an X a little bit, kind of a squashed out or a truncated X. And that's the quad ring there, backed by some recycled milk carton HP high density polyethylene backup rings, they call those. And this is just a little washer there and a big old fat nitrile rubber Buna N typical O-ring, and they use that as a bottoming out squash ring, like a shock absorbing, what would you call that? Bumper, essentially. Now, the first variable displacement, or the first variable volume cylinder, is actually twinned up with a secondary smaller one in the rod itself. And we can see that if we push down, we'll open that guy up. That's quite stiff, so we'll just push that down. You see that bouncing. Now we'll close that valve. What that valve does when you close it is it locks off transfer from one cylinder to another. So we should see this stay down. Yeah, there we go. And we're building pressure in here. Of course, if we put a gauge in this port and took this little, I bet you that's an Allen screw adjustamente. Just bear with me here. I've never had one of these apart, so I'm learning the same as you. Yeah. Oh, and look at that. It's even got a hole in there. So all you got to do is open it up, and that would allow that to extend. And if we want to extend, this is the rebound, recall how quick it rebounds. Tap it, tap, tap. Got her just a boot, fully compressed. We'll stick an Allen saw, a metric no less. Let's see if that pops up. Yeah, you can hear the air escaping. And oh, it sank down. Yeah, of course it sank down because there's nothing countering. We got rid of the spring in there. So if we do this, it doesn't want to go up. We got to manually. Oh God. Well, it done fuckered it proper now. Wonder if that's no user serviceable components inside. What we can do is take that gland nut off. Looks like there's a set screw in here. We'll see if I can get that gland nut off. If not, I'll have to reef it up anyway to take that set screw out. Helps if you go to the right direction. Oop, sorry about that. You didn't need that eyeball anyway. You got two of them for a reason. Oh yeah, and we're losing some fluid in there. Okay. So there is some damping in here because there's a liquid, and a liquid is a virtually non-compressible fluid, whereas air is a compressible fluid. And fluid just means it conforms to the shape of its container. It's a material that conforms to the shape of its container. So something like a jello, not a fluid, because it doesn't melt into the shape of its container, even though it's actually a solid. It's a gel, but it's a solid, not a fluid. And I don't know if something's gonna. Oh man. It's just grin and close your eyes. It's the debutante's ball. Son of a diddly. Oh. Yep. You keep jacking it off till you get a little squirt. Now that is an interesting liquid. You look at that. Drop. It wants to stay together, even though it's not viscous. It's quite thin. I would think that it smells like a kind of mineral oil. I don't think it'd be a silicon. No, that's mineral oil. Some 11 herbs and spices. Pardon me my nerdgasm. This is fucking fantastic because this is just like a shock absorber in your car. Of course, what I was worried about and what I initially thought was this was only an air spring. And of course, when you get an air spring, when it absorbs a shock or when you hit it, it resonates. You don't want that resonating. You want some damping to that. And I'll give you here's a chunk of HSST. I'll put it up to the microphone and give her a whack, and you'll hear it resonating. Now, if you put it on something that has some damping action to it, like this nitrile rubber handled what's its who's it's, and then you give her a whack, it deadens the resonation. So that is what this section is for, this smaller section, oil filled, and we force the oil through that orifice there in the piston itself. And you see, You can't force it in quick. It doesn't want to go. If you force it in nice and slow, it slides easy because you can only flow so much oil, or in this case air, just during the test through that without it fetching up. Pressure spikes, and so that is where we are damping that energy out. Now the thing about it is, why would they not have a lockout on here? Because they already have the valve. So it's really fuck all. This is of course a one-way check valve. It would be fuck all to put another valve on there that ramps, that has a little lever, or you know, a little wedge ramp, rotary wedge ramp, I guess you call that a thread, but a section of thread that forces that one-way check needle in and forces it closed so that you can't transfer air from one cylinder to another. Now some of these guys have quite big air reservoirs, fluid reservoirs, and have an additional little dingus end on here. Why would you want that additional little dingus? Well, that changes the spring rate so that the harder you push a spring, if you want to compress a spring more, you have to push it harder. Well, the slope of that angle from displacement to force is the spring rate, and the more fluid, the more air that you can have in here, the lower that spring rate. I'm running out of time on my card, if you can't tell, and I don't have another one here. So if you got any questions about how this fascinating little piece of machinery, I mean, these things haven't been around for that long, you know, basically developed for the automobile, 100 years. And now we got them on two-wheeled death contrivances, which you got to power with your own sweat. Thanks for watching. Don't buy any wooden nickels from them bicycle marketeering types. Keep your dick in a vice.